Hello, welcome to Noise Management and its Control. Today is the 5th day of this week, and what we plan to do today is conclude our discussion on closed tubes, and maybe if we have time we will start discussion on open tubes. So, yesterday what we had discussed was we had developed these two equations. The first equation is for the pressure wave in a closed tube, and the second equation relates to particle velocity in a closed tube. And then using our definition for specific acoustic impedance, we found that specific acoustic impedance in a closed tube is minus j times z naught cotangent omega x over c. And if I plot this function in an xy plane, this is how my specific acoustic impedance curve is going to look like. Now, the next thing I wanted to discuss in context of these waves is the concept of standing waves. So, before we do that, we will once again write down the equations for pressure and equations for velocity. So, for a closed tube, our equation for pressure is P1 by cosine omega L over C, cosine omega x over C, cosine omega t plus phi, and my particle velocity equals P1 divided by z naught cosine omega L over C sine omega x over C sine omega t plus phi. These are the two equations. Now, what we will do is, first we will make a plot and then we will explain what is the meaning of that plot. So, what we are going to plot is this term. Okay. So, what we are going to plot, so we are going to plot this term, and let us call this term in light blue as some constant C1, because P1 is constant, omega is constant, L is constant, C is constant. So, this entire term is some constant C2, C1. Similarly, this is another constant C2. So, I can rewrite these equations as C1 cosine omega x over C times cosine omega t plus phi, and this is C2 sine omega x over C times sine omega t plus phi. Now, what we are going to do is we are going to plot this term in green, these two terms in green. So, that is my x axis, on the y axis I am going to plot the terms in green. X is equal to 0 at origin, and if you remember, our coordinate system was such that the closed end of the tube, this is the closed end, x is equal to 0, this is negative x and this is positive x. Okay. So, let us call this entire term as A, capital A, and let us call this entire term as B. So, at x is equal to 0, x is equal to 0, cosine of omega x is 1. So, the value will be C1. So, I am just going to do some construction, and then I am going to actually plot this. So, please bear with me for a moment. So, this is plus A and this is minus A, and on the x axis actually I am plotting omega x over c, okay, like this. So, at x is equal to 0, so here this is 0 radians, then I have pi over 2, pi, 3 pi over 2, 2 pi, five pi over 2, 3 pi, and 7 pi over 2, and then this is 4 pi, and again I will just draw some construction lines so that we develop a good graph. Yeah. So, this green curve is for function A, and these things, and the maximum value of this function A is going to be C1, and I incorrectly wrote this earlier, it should be positive C1 and negative C1. So, if I plot this function A, which is C1 cosine omega x over c, it will look like this green curve, okay. It will look like green curve. At x is equal to 0, its value is going to be maximum. At when omega x over c is pi by 2, its value is going to be 0. When it's 3 by 2, again it will be 0, and so on and so forth. What that means is that for different values of x, the maximum pressure, the value of maximum pressure changes. At x is equal to 0, the maximum pressure is C1. At x is equal to some location, when omega x is pi by 2, the maximum pressure at that location is 0. Then if you move further deeper into the tube, so maybe the pressure here is maximum, then pressure here becomes 0, then maximum pressure here becomes again C1, then again pressure becomes 0, and so this is how the amplitude of the pressure is. Now, of course, this is also multiplied by cosine omega t. So, at a given point the pressure fluctuates. So, for instance, if we are looking at this location of x, then the pressure fluctuates between these two limits, okay. Corresponding to this value of x, the pressure fluctuates between this limit and this limit. At some other location, the pressure fluctuates between some other limits, okay. So, the pressure, amplitude of pressure fluctuates between two specific limits, and those limits are defined by function A. That is why this function A is known as spatial envelope for pressure. It is the spatial envelope for pressure. And because the tube is closed, the spatial envelope for pressure has a maximum value at the closed end of the tube where x is equal to 0, and this is how it behaves. Okay. Now, let us look at function b. So, we are going to plot function b in purple color, and the function b is going to look somewhat different. So, at x is equal to 0, function b, because x is equal to 0, its value is going to be 0. So, we start from 0. So, here C2, we assume that C2 is equal to C1, we just assume numerically, otherwise they may be different numbers. C1 has a different unit, C2 has a different unit, but on plot we have to plot something. So, we are just assuming that C1 is equal to C2, that is all. So, if I plot this at x is equal to 0, it is 0, and then when pressure is maximum, pressure amplitude is minimum, velocity amplitude becomes maximum. It goes like this. Okay. Now, these are sinusoidal curves, they may have, I may not have drawn them well enough, but please note that function b. So, this is the purple is function b, and what we see from this graph is that wherever the amplitude for pressure is maximum, at that location the amplitude of velocity is minimum and vice versa. So, the plot for B is called spatial envelope for velocity. Okay. It is spatial envelope for velocity. So, we make couple of observations. One, these types of waves in a closed tube, the pressure fluctuates between two specific limits, and these two limits vary from place to place. These limits are fixed, and but they vary from place to place, and these types of wave, because of that, these types of wave are known as standing waves. They are known as standing waves. Here, for instance, a good example which you can visualize what is a standing wave is that if you tie a rope to a nail which is inserted into a wall, and then you move the other end of the rope up and down, there is wave motion in the rope, but when you look at the pattern of the rope, it appears fixed, and it appears something similar to the spatial envelope for velocity, and it appears fixed and it looks like the wave is not travelling. So, that is why they are known as stationary waves or standing waves. The second observation we make from these graphs is that velocity amplitude is max when pressure amplitude is min and vice versa. Okay, and vice versa. The third thing is that in standing waves, amplitude of pressure varies from point to point. okay, depends on the position. But in travelling waves, and an example of travelling wave would be a wave travelling in an infinitely long tube, it does not get reflected, and in a travelling wave you do not get these kind of equations, you know, you do not get these type of equations. So, in a travelling wave, amplitude of pressure is same everywhere. If we can figure out the solution for a travelling wave, we go back to a couple of lectures earlier. See, this is the equation for a travelling wave which we had developed. This is for a wave which is travelling in an infinitely long tube, and the wave is being generated from this end, and here you have 42 cosine 2t minus 2x by c plus pi over 6. Okay. So, here the amplitude is 42 and it remains same for all values of x and t, right. But in case of standing waves, the term in x and the term in t, they separate out, and that is why, and the term in x is a cosine function of x. So, because of this, the amplitude of the wave which is designated by function a, or the amplitude of velocity waves which is designated by function b, it varies from position to position. Some terminology. So, wherever velocity equals 0, we call it it is velocity null. Wherever velocity is minimum, it is called velocity node. Okay. Now, in our case, the location where velocity is 0 and the location where velocity is minimum is same. Okay. So, in our case, in our example, positions of null and positions of nodes are same. Okay. But there may be some way, the reason why it is happening is because we have a rigid termination. So, whatever velocity is coming, that energy is getting reflected 100%. Okay. But in some waves where reflection is not 100%, the place where velocity is minimum and the place where velocity is 0, they may be different. Okay. So, they may be different. So, similarly, in our case, pressure nulls and nodes occur at same locations. Okay. So, that is the overall picture for standing waves in context of closed tubes. So, I presume that this concludes our discussion on standing waves in closed tubes. Tomorrow is our last lecture for this week, and we will close the discussion tomorrow by having some detailed description of how do sound waves, one dimensional sound waves, they travel in tubes which are not closed, but they are open. So, that is a totally different category, and with that we will conclude the discussion on transmission line equations over this week. So, thank you very much, and we will meet tomorrow.